I now want to discuss something. Turns out that you're now in a position to understand, I would say, one of the greatest discoveries in physics in the last 50 years. We're going to learn about that discovery now. I won't tell you exactly what it is yet, and then we'll see how it comes about. So we're going to take a look at a typical galaxy and imagine the mass inside the galaxy is causing the stars around that galaxy. They rotate around the galaxy. So for instance, our sun rotates around the galaxy, and I think one of the homework problems asks you how many years it takes for it to go all the way around in its orbit around the center of the galaxy. So there's a lot of mass inside each galaxy in the universe. And there's a very mysterious result about that. And let's see what that result is. So we're going to start with Newton's second law. And just to make things easy, we're going to assume circular orbit. And we're going to assume, even though this is not quite right, it's good enough, spherical mass distribution. I mean, it's not quite right. For instance, our galaxy is a spiral galaxy, and there's some mass in the middle. There are these spiral arms. But for the argument we need today, we'll just do things the simple way. One could do the calculations in a more complicated way, but the basic idea can be gotten this way. All right, so Newton's second law. We have the gravitational force on a star. So on any star, it'll be G. This is the mass in the galaxy. And it's the mass enclosed within the orbit of that star. Okay? Any mass outside the orbit of that star, if it's a spherical distribution, the forces due to them will cancel out. So there's that. Then the mass of the star, and then we divide by the radius squared. So that's the position of the star relative to the center of the galaxy. All right? And since it's going in a circular orbit, we can write this as m star v squared over r. So that's all we need for this fantastic discovery that I'm going to tell you about. So I'm going to solve for v. So I get v squared. The m stars cancel out. This cancels with this. And you get g times the mass of the galaxy. All right, what else is there? There's an r over r, right? Or v is equal to the square root. All right. So what this means is that if we look at stars that are kind of near the edge of the galaxy, or even, there are a few stars that are actually a little bit far away from all the visible mass or most of the visible mass of the galaxy, right? So if we look at them and we plotted v versus r, we should get a curve that kind of looks like this. All right? Falls off as 1 over the square root of r. Okay? So this plot is for stars, let's say outside most of the galaxy. Now, how do you measure these things? Right? How do astronomers actually measure this? So r can be measured within a galaxy. You can measure r measured using what's called parallax. I won't go into the details. But the basic idea is you look at the position of the star let's say on January 1st, and then you look at it at, let's say, 6 months later, when the sun has gone around, when the Earth is going around the sun, and the position of the star will be slightly different in the sky. And using some geometry, that'll tell you how far away it is. The further it is away, the less its change in position in the sky. This is geometry. If you take an astronomy course or if you look up on the web under parallax, it'll show you how to do that. The velocity is measured using what's called the Doppler shift. So this is one of the most important tools in physics, especially in astronomy. All right, we use the Doppler shift to know, for instance, that the universe is expanding. So what the Doppler shift is, how many people have ever heard a train whistle? Nobody? A train whistle? Never? Trains don't ever make sounds? Like when they're coming into town? Or something like that? Or you're waiting for a train and you see it? So if you listen to a train whistle, when the train is coming towards you, the tone or the pitch goes up. Eee! Up. All right? And if it's going away from you, it goes down. Ooh, ooh, down. All right? The pitch goes down. That is due to what's called the Doppler shift. The same thing occurs for light. If light is moving away from you, its color will be shifted towards the red. Its wavelength gets bigger, and its frequency goes down. If it's coming towards you, then its color goes towards the purple end, the blue end. The frequency goes up, wavelength goes down. That's called the Doppler shift. Now, of course, it's a little tricky because you have to figure out what direction the star is going, but one can more or less do that. And how do people measure this shift? Well, stars are, like our sun, they are burning hydrogen and helium and other elements. And so when you look at their light through what's called a spectrograph, you see spectral lines that are due to specific atomic transitions. Hopefully you'll learn about this in chemistry if you haven't already. All right? And these lines are shifted slightly due to the Doppler shift. So it's very easy to measure velocity very accurately using these Doppler shifts. All right? So in 1975, an astronomer, Vera Rubin, who actually met once about 25 years ago, measured the velocity of the stars near the edge of our galaxy and further behind, but afterwards, and also that of other galaxies. So she measured velocities of stars that are near the edge or further out on the galaxy. And what she found was not this. What she found is the velocity was pretty much constant as you went further and further out. This was an astounding discovery. Why? Because it meant that the mass that they were seeing in the galaxy, the visible mass, was not all the mass in the galaxy. Because there's a tremendous amount of more mass out here that's essentially keeping this M galaxy bigger and bigger as you get further and further away, even though you couldn't see these stars or whatever it was. So there was mass there that nobody could see with telescopes. It wasn't visible. So this mass was not coming from stars, because stars are visible, and you can see all the stars, you can figure out what their masses are, etc. All right? So there's mass in the galaxy, huge amounts of it. In fact, much more mass than the stars themselves. And the vast majority of mass in our universe is unseen. And this mass is called dark matter. All right, so this is the dark matter discovered by Vera Rubin in 1975 is when she reported it. All right, so it's the missing mass. It accounts for roughly 20% of the total energy in the universe. All right, visible mass is only about 5%. So most of the mass in the universe is not seen, and we have no idea what it is. Absolutely none. Some of the ideas that people have suggested are that this mass might be neutrinos, all right? Or small black holes, tiny black holes, all right? The reason why they suggest these things, and it can't be things like hydrogen or helium or something like that, because those things would interact. We would be able to see the effects of those very easily, because when light came to us from another galaxy and went through the dark matter, it would be absorbed and re-radiated and stuff like that. And we don't see any of that. All right? So that whatever is this dark matter is not regular matter. All right? It's not protons and neutrons and things like that. Now, people thought it might be neutrinos, but that's been pretty much ruled out, because they can measure neutrinos. We can see, we can detect neutrinos, and there has not been an excess of neutrinos detected. All right? Small black holes, that has problems too, because these small black holes will evaporate, and that'll give some signature that they're there. Nobody's seen that. All right? A number of groups around the world are trying to look for this dark matter. They have huge vats of fluid. And the basic idea is they look at every single interaction that occurs in the fluid, and then they look for ones that have signatures that they've never seen before. It's like looking for a needle in the haystack when you don't even know what the needle is. You don't know whether it's a needle, whether it's a pea, whether it's some other thing. You have no idea what it is. And they're trying to look for it. So there are a significant number of groups, big money going into trying to look for it. And they've been doing this for, I don't know, maybe 10 years now, and nobody has found anything. All right, so nobody knows what it is. Now, you remember that story I told you about Mercury and how Mercury's orbit wasn't quite right, and they thought there might be a planet between Mercury and the sun? This smells like that. All right? So the solution to that problem was to fix our theory of gravity. So there's yet another group of people who are trying to fix the present theory of gravity, the general theory of gravitation, general theory of relativity that Einstein first put forth. Okay? However, that hasn't gone very well. All the suggested changes that might account for dark matter would lead to effects that we do not see. General relativity works extremely well. and is even working better now than it ever has because of the discovery of gravitational waves, which is just working perfectly, just like we expected for the theory. All right? So that approach is not going well either. So if you ask astronomers what the biggest mystery in the universe is right now, I'd say a lot of them would probably say this. There's also dark energy, which they also have no idea what that is. All right? And there are all kinds of theories about that, but they don't know what that is either. So if this is not discovered, if they don't figure this out in the next 20 years or so, I don't know what's going to be, okay? Because they should have some idea what it is, all right? And unfortunately, there are not too many ways of figuring it out, all right? And all it takes is basically the kind of physics that we've discussed here. I mean, there's little details because it's not perfectly spherical, but you can easily account for those, all right? And of course, doing these measurements, measuring the distance r and the velocity v, we know how to do it. We're very good at it. Not me necessarily, but astronomers are very good at it. All right? And there's no doubt, there is absolutely no doubt that there's something going on there. And by the time you grow up, older, 20 years from now, you might know the answer. All right? Hopefully, we will. Whether I'll know the answer, I don't know. So we want to talk, what is a fluid? Water is an example. Air is an example. Okay? So there's a distinction. A fluid is gas or a liquid. So this is like air and like water. Okay? So we can treat both of them, both gases and liquids, using the same ideas. All right? So we call them fluids. So what is a fluid? What are characteristics? What distinguishes a fluid from, let's say, a solid, or from nothing? What is it? Any ideas? All right. First of all, fluids, the word fluid, it kind of flows. All right. Fluids can flow, whereas a solid usually stays still. I think everybody here knows what it is. You know, they can see it when they know it. They can tell. You don't need an actual definition. All right? Now, there are three quantities that define the property of a fluid at a particular location. So there are three properties of a fluid at each location. So the first property that we're going to is density. All right? In density, we use the symbol rho, and that's the mass per volume. All right? So this is called rho. All right? So you take a piece of your gas or liquid, piece of your fluid with a certain volume. You measure how much mass there is in there. That gives you the density. All right? The density of water is about 1.0 grams per centimeter cubed. Okay, so it's 1 gram per centimeter cubed. In fact, I think to some degree that's how the gram was defined. All right, now we can think of density as varying from one place to another, but I think in almost everything we do today, the density will be the same everywhere. Okay, so it's pretty much a constant. So for instance, the air in this room, the density over here is about the same as over there. It's not much different. The density of water or blood in your body doesn't change that much. All right? It's pretty much the same from your toes to your head. All right? So density does not change a lot in most of the problems we're going to be talking about. But it can. All right? I could take a container of air, and I could have like a plunger, and I could push into it, and I will get a much denser amount of air. It's a lot harder to do that with a liquid. Right? Why is that? Because the compressibility, it's hard to compress it. The bulk modulus is not as what? Is the bulk modulus big or small? I can never remember which way it goes. But the compressibility of air is large. It compresses easily. For a liquid, it does not. It's very hard to compress a liquid. All right, so this is density. So every point in space, there's a density. The second quantity is pressure. All right, we brought this up once before when we talked about the bulk modulus. And remember, the pressure is equal to the force per unit area. All right, so you imagine some little area here. This has area A. All right, and then if there's a force on it, the force per unit area tells you the pressure right there. Now, unlike the density, the pressure does vary quite a bit. For instance, even in my body, the pressure at my foot is higher. My blood pressure is higher at my foot than it is in my head. Right? So pressure varies from spot to spot, and we'll learn how it varies in a minute. But every spot in the universe, even, any spot in the gas has a pressure. There's a pressure over there. There's a pressure over there. There's a pressure there, pressure there. Every spot has a pressure. Pressure is not a vector, though. All right? For us, it's going to be a scalar. Even though it has this force per area, and force is a vector, we're really kind of like dotting the force into the area vector. So it's really it's a scalar. We don't talk about the direction of the pressure. Every point in space has a pressure. So if you can think of that pressure as kind of pushing out in all directions. In fact, that's a good way of thinking of pressure, as a kind of pushing out of the fluid. All right? So if you have a container, the pressure of the gas pushes out on the walls of the container. All right? And the way you would measure it is by looking at the force. You would have to put a surface there, measure how much force there is on that surface, and that would give you the pressure. All right, some numbers. This at Pascal is 1 unit of pressure, and that's 1 Newton per meter squared is a Pascal. The air is 1 atmosphere, and that's about 10 to the 5th newtons per meter squared. or 10 to the 5th Pascal. So it's quite big, even though it's just air. Why is it so big? Well, there's a lot of air. There's a lot of air on the surface of the Earth. All right, so let's see how much force there is on your head. So the force would equal pressure times area. So we have 10 to the 5th is the pressure. And what's your area or head? Here, let's measure it. All right. So his head is about 15 by maybe a little over 20. So let's say 300 square centimeters. All right? I don't know if that's big or small. Okay. So 300 square centimeters, how many square meters is that? How many centimeters in a meter? How many? 100. So to get from square centimeters to square meters, we have to divide by 10,000, right? 100 times 100. So what's 300 divided by 10,000? Right, it's 0.03. So I multiply that. So 10 to the 5th, 10 squared will give me 3. So that's like 3,000 newtons. That's a lot of force on the top of your head. 3,000 newtons. So that, yeah, that's 300 kilograms. Right. So imagine 300 kilograms. That's a big, solid piece of iron, right? Sitting on the top of your head as you walk around. So why don't you get a headache? There's a lot of force on your head. Well, the reason is inside your head, your blood, the air in your body, everything is also pushing with the same pressure, roughly. So the pressure on the top of your head is balanced by the pressure inside your body. And so you don't feel anything, right? Only under certain circumstances can you really tell that this is going on. For example, if you go deep sea diving, all right, if you come up too quickly, all right, so first you go down, and your body equilibrates to the pressure in the water. The water pressure is higher down below than it is in the air, so there's pressure on your body. So inside your body adjusts to that and builds up its own pressure. And then when you come up, if you come up too fast, it doesn't have time to equilibrate, and it hurts. You get what are called the bends, all right? Because you came up too quickly. None of you have to worry about that unless you dive like over 100 meters or so, all right? Something like that, all right? So that's a real effect, all right, is that. Suction cups work the same way. If I take a suction cup and put it on this table, right, I can make it so it's very hard to pull it up. How does that work? Well, it's because you have this amount of newtons, or maybe half that if it's smaller, right? Because you've sucked out the air under the suction cup. So there's no pressure up, there's only pressure down on the suction cup. All right, so all kinds of sort of suction effects work that way. So this pressure is real. It really is there. Now in principle, when we did all our mechanics before, all those problems you did, we should have added in these forces. But again, these forces would cancel out in almost every case. Very rarely do they not. All right. So that's the second property. The third property, which we'll talk about later in the class today, is velocity. So at every point in space, the fluid as a whole has a velocity. I'm not talking about the molecular motion. The individual molecules might be going back and forth, but the overall flow of the fluid. It's kind of like an average over all the molecules. And this can vary with position as well. And we'll talk about that near the end of today's class. All right, so you have three properties at every point in space: density, pressure, velocity. Each of those is like a field, like the gravitational field, because it's a property of space. It's a property of your location in space. All right? OK, so that is what we need to get started. So one of the most important things to figure out is how the pressure varies from location to location. In particular, how it varies with depth. OK? So let's see how that works. We want to know how the pressure varies with depth. So here's my fluid. We'll say we have a pressure P0 up there. That'll be usually atmospheric pressure that we have over there. And let's consider a certain volume here. It has a cross-sectional area A and a depth H. All right, so the volume is A times H. So the question is, what is the pressure right here? What's the pressure at this location on this? All right, so we can figure that out. That piece of water or fluid is just sitting there. It's not moving. So if that's the case, what can you say about the net force on this little volume of fluid? What's the net force on it? What's it got to be if it's not moving? 0. So the net force is 0, right? So let's figure out what all the forces on the object are. So we draw a free body diagram. All right? So can anyone tell me an example of a force on that piece of fluid? Gravity. All right? So we have mg, and that's down. Usual thing. All right? Anything else? Now remember, we're considering the forces due to pressure. So what else is there? Why does it? There's got to be other forces, otherwise that piece of water will flow down. And it's not. When I have a glass of water, the water just stays there. I don't notice the water on the top moving down. Where's the pressure coming from? Where is it? What was that? Is that what? From the water. Where? Which direction is it? There's a pressure up. Is there a pressure on this surface? Yeah, so there's a pressure up. All right? So the pressure is P here. That's what we're trying to figure out. What's the force? Looking at the symbols on the diagram, what's the force going up? What? PA. All right. What about the pressure on this surface? Is there a pressure here? Pushing this way? Is there? Yes. And that's balanced exactly by a force on the other end. They're just going to balance each other. All right, so those balance out. All right, is that the only pressures? Is that the only forces? All right, so the force is this P0 here, right? That's atmospheric pressure. Which direction is that? Down. So we have another force down, P0 times that. Are there any other forces? Or is that it? All right, that's it. All right, so the sum of the forces has to equal 0. I'll just do the y component. So we have PA up, and then these two down, minus P0A minus mg equals 0. Okay? Now this mass here is rho times the volume, right? Mass per unit volume times volume, right? So how much volume is there here? There's A times H. So this is rho A H. Okay, so I stick that in. I get PA minus P0A minus rho GH, rho GHA equals 0. All right, so I have a rho AH, rho AHG. All the A's cancel, and I get my result. P equals P0 plus rho GH. All right, so we get that result. All right, so that says the pressure increases with depth. H is a positive quantity. It's saying how much you're going down. So this is how the pressure varies with depth. All right. Now we could do the same thing if we stick an object in here. So let's stick an object there. So this is an object of mass m. It's not the water. It's not the fluid. Maybe I'll make it m0, object. All right, so there's a pressure here. We'll call this, I don't know, P2. Pressure here, P1. And using the same exact logic, we get P2 times A, the pressure up, minus the pressure down, minus the mass of the object times G is equal to 0. And this force, this is a force, that's called the buoyant force. That is what the buoyant force is. All right, so that's the buoyant force. We can calculate what that is based on all this calculation. We know that the pressure difference, P2 minus P1, equals rho GH. All right? So if I stick that in here, I get that the buoyant force is rho GH times A. All right? And that's usually written the mass of the water displaced times G. So that's the mass of fluid, I'll write, displaced. All right, so that's, remember, this rho is not the density of the object. It's the density of the water or the fluid. So the buoyant force is equal to the mass of the water that that object takes up in the fluid times g. All right, now there's one little tricky part here, and that is, what if the object is not fully submerged? Which is what happens like for a ship. All right, so what if we have an object like this? All right, and we have a depth h here, we have an area there. All right, what happens then? All right, so let's do the usual thing. We have a pressure here. All right, so we have a pressure P0 here. So we have PA minus P0A minus mg equals 0. All right? And this, again, is the mass of the object. Right? So there's a gravitational force and two pressures causing forces. But we know that the pressure over here is just equal to P0 plus rho gh. So this is P plus rho gh, P0 plus rho gh times A minus P0A minus M0G. All right? P0 times A cancels, so we get rho GHA. So here again is our buoyant force. And notice again, it's the mass of the water displaced equal to rho HA, volume, not of the object, but of the water displaced, right? It's only this amount of volume that goes into the buoyant force. So that's very important. When I write that the buoyant force is equal to the mass of the water displaced times g, this is only the part of the fluid that's underwater or inside the fluid. And this is what ensures that a ship does not sink. Even though the ship has got a huge mass, there's a lot of air inside of the mass. Same with your body. All right? So if you want to kill someone and get rid of the body, you have two choices. One, you put a bunch of rocks, tie rocks to them. The other is you just replace the air in their lungs with water. All right? Because the only reason they float, the only reason you float in water is because you have air inside your lungs, and that has a much lower density. All right? So your weight here, all right, is not as big as the weight of water. Okay? Water is pretty heavy. All right? If you tried to pick up somebody with your volume and purely out of water, I think it would be heavier than you yourself. All right? Okay. All right. So that's what's called static equilibrium. You just do the same thing you always do in Newton's second law. All you got to do is stick in the buoyant force, add that in, and then you're done. All right. So we want to look at what happens when the fluid is flowing. Okay? So here we're going to take 2 points in the fluid, and we're going to see how those 2 points change. And they could do it in many different ways. You can have a tube like this, and the tube can expand up like that, and then come down, and then it could go down like this. There are all kinds of things like that. And at each point, you'll have a velocity. We could call this v1, v2, v3, and then all along here, the velocity will change. So there are two important results that you have to know. One is the fluid here, when it comes out here, it expands up here, right? So that means the velocity here has got to be faster or slower than the velocity here? Faster. Why? Because the amount of fluid flowing has to be the same. All right? So if I take a little piece of fluid over here, when it gets over here, this amount here must be the same here. The only way for that to be is if this guy is thinner. So that means the same fluid here is going slower. Right? And this is called continuity. So as long as the fluid is incompressible, which is what water to a good degree is, that's going to be the case. So that's continuity. Then we have one other result. So far, we've used Newton's second law. Now let's use conservation of energy. All right, so let's look at energy considerations with fluids. So I'm going to look at the energy density at each point. Energy density. So the kinetic energy will just be 1/2 mv squared. And then if I want the density per unit volume, I just divide by v. M over v is density, so I get 1/2 rho v squared. So that's the kinetic energy density. Okay? We can also look at the potential energy density. So this is kinetic energy density, and we can look at potential energy. So how would you do that? This would be, so potential energy divided by volume. So it would be mgh divided by v. So this is the mass of some piece of water divided by the volume of that water. So that's just rho gh. All right, so now we have the kinetic energy, and we have the potential energy density. All right, the third thing we might want to know is how much work is done by the pressure. And we also want to divide that by density. You know, work is F times some little delta x, right? Force times distance. You divide by v to get the density of that work. Force is pressure times area, divided by v. And so that's just equal to the pressure. Because A times delta x is the little bit of volume of the fluid. All right, so we have these three densities, energy densities. We have this, we have this, we have this. We add them all up by conservation of energy. We should be the same at every point in space. All right, so we get this equation. P plus 1/2 rho v squared plus rho gh. Is that what I got there? Rho gh, yeah. Is constant. All right, and this is called Bernoulli's. So you have this result here, and we have this result here. So Bernoulli's law is useful in a lot of contexts. It's actually, I'm not going to talk about certain issues because there's a lot of misunderstanding about how it's used. For example, when a plane takes off, it's much more complicated than Bernoulli's law. However, once the plane is in the air, the wings adjust in order to go up and down. They adjust in order to change the velocity flow over the wing. So if they make the velocity flow of the wing lower on the bottom of the wing, then the pressure will be higher than it is on the top. And that can give you lift. And if the velocity is done the other way, you can make the plane go down. So Bernoulli's law more or less tells you what's going on once the plane is in flight. But getting up there, there's a lot more going on. All kinds of boundary effects and things like that. All right.